This lecture is about the similarity-based approaches to text clustering. In this lecture, we're going to continue the discussion of how to do text clustering. In particular, we're going to cover a different kind of approaches than generative models, and that is similarity-based approaches. So the general idea of similarity-based clustering is to explicitly specify a similarity function to measure the similarity between two text objects. Now, this is in contrast with a generative model where we implicitly define the clustering bias by using a particular objective function like a likelihood function. The whole process is driven by optimizing the likelihood. But here we explicitly provide a view of what we think are similar. And this is often very useful because then it allows us to inject any particular view of similarity into the clustering program. So once we have a similarity function, we can then aim at optimally partitioning the data into clusters or into different groups and try to maximize the intragroup similarity and minimize the intergroup similarity. That is to ensure the objects that are put into the same group to be similar, but the objects that are put into different groups to be not similar. And these are the general goals of clustering, and there's often a trade-off between achieving both goals. Now, there are many different methods for doing similarity-based clustering. In general, I think we can distinguish two strategies at high level. One is to progressively construct a hierarchy of clusters. And so this often leads to hierarchical clustering. And we can further distinguish two ways to construct the hierarchy depending on whether we start with the collection to divide the collection or start with individual objects and gradually group them together. So one is bottom-up, that can be called agglomerative, where we gradually group similar objects into larger and larger clusters until we group everything together. The other is top-down or divisive. In this case, we gradually partition the whole data set into smaller and smaller clusters. The other general strategy is to start with the initial tentative clustering and then iteratively improve it. And this often leads to a flat clustering. One example is k-means. So as I just said, there are many different clustering methods available, and a full coverage of all these clustering methods would be beyond the scope of this course. But here we're going to talk about the two representative methods in some detail. One is hierarchical agglomerative clustering, or HAC. The other is k-means. So first, let's look at the agglomerative hierarchical clustering. In this case, we're given a similarity function, of course, to measure similarity between two objects. And then we can gradually group similar objects together in a bottom-up fashion to form larger and larger groups, and they also form a hierarchy. And then we can stop when some stopping criteria is met. It could be either some number of clusters has been achieved or the threshold for similarity has been reached. There are different variations here, and they mainly differ in the ways to compute a group similarity based on the individual object similarity. So let's illustrate how we can induce a structure based on just similarity. So start with all the text objects, and we can then measure the similarity between them, of course, based on the provided similarity function. And then we can see which pair has the highest similarity, and then just group them together. And then we're going to see which pair is the next one to group. Maybe these two now have the highest similarity. And then we can gradually group them together. And then every time we're going to pick the highest similarity pairs to group. Right? This will give us a binary tree eventually to group everything together. Now, depending on our applications, we can use the whole hierarchy as a structure for browsing, for example. Or we can choose a cutoff, let's say cut here to get 4 clusters. Or we can use a threshold to cut. Or we can cut at this high level to get just 2 clusters. So this is the general idea. Now, if you think about how to implement this algorithm, you will realize that we have everything specified except for how to compute the group similarity. We are only given the similarity function of 2 objects, but as we group groups together, we also need to assess the similarity between 2 groups. And there are also different ways to do that. And there are the 3 popular methods are single link, complete link, and average link. So given 2 groups, and the single link algorithm is going to define the group similarity as the similarity of the closest pair of the 2 groups. Complete link defines the similarity of 2 groups as the similarity of the farthest pair. Average link defines the similarity as the average of the similarity of all the pairs of the 2 groups. So it's much easier to understand these methods by illustrating them. So here are 2 groups, G1 and G2, with some objects in each group. And we know how to compute the similarity between 2 objects. But the question now is, how can we compute the similarity between the 2 groups? Right? And then we can, in general, base this on the similarities of the objects in the 2 groups. So in terms of single link, and we're just looking at the closest pair. So in this case, these 2 pair objects would define the similarity of the 2 groups. As long as they are very close, we're going to say the 2 groups are very close. So it's an optimistic view of similarity. The complete link, on the other hand, will be in some sense pessimistic, and by taking the similarity of the 2 farthest pair as the similarity for the 2 groups. So we are going to make sure that if the 2 groups are having a high similarity, then every pair of the 2 group, the objects in the 2 groups will be ensured to have high similarity. Now, average link is in between, so it takes the average of all these pairs. Now, these different ways of computing group similarities will lead to different clustering algorithms, and they will in general give different results. Now, so it's useful to take a look at their differences and to make a comparison. First, single link can be expected to generate loose clusters. The reason is because as long as 2 objects are very similar in the 2 groups, it will bring the 2 groups together. If you think about this is similar to having parties with people, then it just means 2 groups of people would be partying together as long as in each group there is a person that is well connected with the other group. So the 2 leaders of the 2 groups can have a good relationship with each other, and then they will bring together the 2 groups. In this case, the cluster is loose because there's no guarantee that other members of the 2 groups are actually very close to each other. Sometimes they may be very far away. Now, in this case, it's also based on individual decisions, so it could be sensitive to outliers. The complete link is in the opposite situation, where we can expect the clusters to be tight. And it's also based on individual decisions, so it can be sensitive to outliers. Again, to continue the analogy to having a party of people, then complete link would mean when 2 groups come together, they want to ensure that even the people that are unlikely to talk to each other would be comfortable with talking to each other. So ensure the whole cluster to be coherent. The average link, of course, is in between, and it's group decision, so it's going to be insensitive to outliers. Now, in practice, which one is the best? Well, this will depend on the application, and sometimes you need loose clusters and to aggressively cluster objects together. Then maybe single link is good, but other times you might need tight clusters, then complete link might be better. But in general, you have to empirically evaluate these methods for your application to know which one is better. Now next, let's look at another example of a method for similarity-based clustering. In this case, which is called k-means clustering, we will represent each text object as a term vector, and then assume a similarity function defined on two objects. Now we're going to start with some tentative clustering result by just selecting k randomly selected vectors as centroids of k clusters and treat them as centers, as if they represent they each represent a cluster. So this gives us the initial tentative clustering, and then we're going to iteratively improve it. And the process goes like this. And once we have these centroids inside, we're going to assign a vector to the cluster whose centroid is closest to the current vector. So basically, we're going to measure the distance between this vector and each of the centroids and see which one is closest to this one, and then just put this object into that cluster. Now this is to have tentative assignment of objects into clusters, and we're going to partition all the objects into k clusters based on our tentative clustering and centroids. And then we're going to recompute the centroid based on the allocated objects in each cluster. And this is to adjust the centroid. And then we can repeat this process until the similarity-based objective function, in this case, it's within cluster sum of squares, converges. And theoretically, we can show that this process actually is going to minimize the within cluster sum of squares, well-defined objective function, given k clusters. So it can be also shown this process will converge to a local minimum. Now, if you think about this process for a moment, it might remind you the EM algorithm for mixture model. Indeed, this algorithm is very similar to the EM algorithm for the mixture model for clustering. So more specifically, we also initialize these parameters in the EM algorithm. So the random initialization is similar. And then in the EM algorithm, you may recall that we're going to repeat E step and M step to improve our parameter estimation. So in this case, we're going to improve the clustering result iteratively by also doing two steps. And in fact, the two steps are very similar to EM algorithm in that when we allocate vector into one of the clusters based on our tentative clustering, it's very similar to inferring the distribution that has been used to generate the document in the mixture model. So it's essentially similar to E step. So what's the difference? Well, the difference is here we don't make a probabilistic allocation as in the case of E step, but rather we make a choice. We're going to make a call. If this data point is closest to cluster 2, then we're going to say you are in cluster 2. So there's no choice, and we're not going to say you are 70% belonging to cluster 2. And so we're not going to have a probability, but we're going to just put one object into precisely one cluster. In the E step, however, we do a probabilistic allocation, so we split the counts, and we're not going to say exactly which distribution has been used to generate a data point. Now the next, we're going to adjust the centroid, and this is very similar to M step where we re-estimate the parameters. That's when we'll have a better estimate of the parameter. So here we'll have a better clustering result by adjusting the centroid. And note that the centroid is adjusted based on the average of the vectors in the cluster. So this is also similar to the M step where we do counts, pull together counts and normalize them. Well, the difference, of course, is also because of the difference in the E step. And we're not going to consider probabilities when we count the points. In this case, for k-means, we're going to only count the objects as allocated to this cluster. And this is only a subset of data points. But in the EM algorithm, we in principle consider all the data points based on probabilistic allocations. But in nature, they are very similar. And that's why it's also maximizing a well-defined objective function. And it's guaranteed to converge to a local minimum. So to summarize our discussion of clustering methods, we first discussed model-based approaches, mainly the mixture model. And here we use an implicit similarity function to define the clustering bias. There's no explicitly defined similarity function. The model defines clustering bias. And the clustering structure is built into a generated model. That's why we can use potentially a different model to recover different structure. Complex generative models can be used to discover complex clustering structures. We did not talk about it, but we can easily design a generative model to generate hierarchical clusters. We can also use prior to further customize clustering algorithm to, for example, control the topic of one cluster or multiple clusters. However, one disadvantage of this approach is that there is no easy way to directly control the similarity measure. Sometimes we want to do that, but it's very hard to inject such a explicit definition of similarity into such a model. We also talk about similarity-based approaches. These approaches are more flexible, directly specify similarity functions. But one potential disadvantage is that their objective function is not always very clear. The k-means algorithm has a clearly defined objective function, but it's also very similar to a model-based approach. The hierarchical clustering algorithm, on the other hand, is harder to specify the objective function. So it's not clear what exactly is being optimized. Both approaches can generate the term clusters and document clusters. And term clusters can be, in general, generated by representing each term with some text content. For example, take the context of each term as a representation of each term, as we have done in paradigmatic relation learning. And then we can certainly cluster terms based on actually their text representations. Of course, term clusters can be generated by using generative models as well, as we have seen.